All right, so at this point we understand that a space outside the nucleus where you can find electrons is designated by three quantum numbers: principal quantum number, angular momentum quantum number, and a magnetic quantum number. So when we have an x, y, and z axis, right, that point in the middle there represents where the nucleus is. So outside of that point, we find the 1s orbital, right, a certain distance from the nucleus. And it's defined by 100, right? That would be the address for the 1s orbital. First energy level, S shape, zero orientation. And then that's it, right? There's only one space to put electrons in the first energy level. We go to the second energy level, we have the 2s position, right? A sphere shape again, designated by 200. Then we introduce the P shape, right, in the second energy level, right? And there's three orientations. An L number of 1 represents a P shape. So we could have a -1 orientation, we could have a 0 orientation, or we could have a +1 orientation. So again, these sets of quantum numbers define places where we can find electrons around the nucleus. Now, looking at this thing, it's hard to see. Well, how do you make sense out of this in terms of these distributions of where the electron's likely to be? So we simplify it by doing what's called the box notation. The boxes indicate the spaces where you're likely to find an electron. So there's a 1s box, and again, potential energy is running up the y-axis here. So because I'm closer into the nucleus, that's a lower potential energy. So the 1s is a lower energy than the 2s. Because of its shape, the 2p is a higher potential energy than the 2s. And again, in the first energy level, we have one place to put electrons, the 1s orbital. When we get to the second energy level, we now have 4 places to put electrons. When we get to the third energy level, we introduce the D shape. We have 9 places to put electrons in the third energy level, and so on. The periodic table of elements, the ultimate tool in chemistry. There are only so many atoms in the universe, and here they are. The way this table is laid out is I can tell a lot about a element's chemical and physical properties just where it's positioned on the table. We already know this. At this point in the course, we've used this table a lot. So just to summarize, right, there's a lot of information that can be gleaned from this particular table, right? So they're giving me the the weighted average of the isotopes. They're giving me what phase the atom is in and at a particular temperature, well, at standard temperature and pressure. They're color coding it for me between the metals and the nonmetals and the metalloids. So we're going to simplify this. I just want to look at this in terms of how it equates to quantum mechanics, how it equates to position of the electrons around the atom. So we're going to have a much simpler periodic table here. So as we know, on this side of the periodic table, we have the periods listed, right? So the first period, the second period, the third period, and we go across the horizontal rows when we talk about period. Going down a group, right, we have group 1A, group 2A, right, the group 1A metals, and then we've got the transition metals, and then we go over to group 3A metals, and then you cross over that magic line that we're no longer a metal anymore, we're a non-metal, and you've got group 4A, 5A, 6A, 7A, 8A. Okay. As we go across a period, we increase in electronegativity. All right, so we understand this, right? How hard an atom pulls on another atom's electron. As I go down a group, I decrease in electronegativity. So fluorine's the most electronegative element. That would be the first element at the top in group 7A, and francium down in that lower left-hand corner would be the least electronegative element. And again, electronegativity was kind of our guide as to writing chemical formulas, right? The more electronegative element went second in the formula, and depending on whether it was an ionic compound or a molecule, we used counting prefixes and so on. All right, so this is our basic understanding at this point of the periodic table. All right. The periods represent the principal quantum numbers. The first energy level and then I drop down to the second energy level, and then I drop down to the third, the fourth, the fifth, and these represent distances from the nucleus. All right, so quantum mechanics, right? Principal quantum number, distance from the nucleus. So in the first period, these represent electrons in the first energy level. And then we go across the second period where we put electrons in the second energy level, and then the third energy level, and then the fourth, the fifth, the sixth, and the seventh. All right, so again, principal quantum number is distance from the nucleus. So as I put electrons into the first energy level, right, there's only one shape associated with the first energy level. That's the S shape. So if we're talking about hydrogen, right, the first element on the chart, it's number one because it has one proton. If you have one proton, you have one electron. Where does that one electron go? It goes into that 1s shape. And when we're putting electrons into these spaces, we're talking about ground state, right? Not electrons that have been zapped with energy and are out at subsequent higher energy states, excited states. When we write electron configurations, we talk about ground state, lowest energy possible. So this would represent where the electron would be in the ground state of hydrogen. You'd find it in the 1s orbital, and that arrow represents a spinning electron. So we put the first electron spinning in an orbital as spinning up. When we get to helium, there's room in that box for 2 electrons. As long as it's spinning in the opposite direction, according to the Pauli exclusion principle, I can put 2 electrons in a space as long as they have opposite spins. This would be the ground state electron configuration for helium. We've got 2 electrons to account for to match up with that positive 2 charge, those 2 protons in the nucleus. And this would be a representation of the ground state electron configuration, the box electron configuration for helium. 2 electrons in the 1s. Now when I get to lithium, I introduce the second period, the second energy level. There are 4 places to put electrons in the second energy level. There's an S with one orientation, and then there are 3 P's with 3 different orientations. So 4 places total to put electrons into the second energy level. So if I'm talking about lithium, because of its shape, a 1s shape is considered a more penetrating shape, a lower potential energy shape. Allows the electrons to get closer to the nucleus. So that electron in the ground state would reside in that 2s orbital. When I get to beryllium, off-bow principle, right? If I'm putting electrons into these spaces, we start with lowest energy first, and then we go to next energy level. So this would be the electron configuration for lithium, ground state electron configuration. When I get to beryllium, there's still room in that 2s for another electron. So as long as the electron is spinning in an opposite direction, I can get 2 electrons in that 2s. They go into the 2s because it's a lower energy. Because of that S shape being the way it is, it's a lower potential energy shape than the 2p. So I've tried to show that, right, by putting the 2p up a little higher, right? Think of potential energy as running up the y-axis of this, this graphic here, right? So the 2p is a higher potential energy shape than the 2s. So when I get to boron, this is when I start putting electrons into those p, those dumbbell shapes. So that first electron goes into the 2p, so the 1s is filled, the 2s is filled, and that next electron would go into that first 2p, spinning in the up direction. Now here's the thing. When I get to carbon, right, it has 6 electrons to account for. Will that 6th electron double up in that already occupied 2p, or will it occupy its own space? And the answer is, it always occupies its own space. Spinning in parallel direction, right? This is called Hund's rule. The most stable configuration for electrons is when the energies are the same, right? This is called being redundant or degenerate, I should say. So those 2p shapes, doesn't matter x, y, or z orientation, they're all the same energy. So electrons will singly occupy before they start doubling up. So the way you would phrase this with carbon on a test question is, how many unpaired electrons are there in carbon? Well, there's paired electrons in the 1s, the 2s, and when I get to the 2p, there's 2 unpaired electrons with carbon. And then there'd be 3 unpaired electrons with nitrogen. Now at this point, we've run out of singly occupied degenerate orbitals, right? So the next electron with oxygen will have to double up, and then we'd have to double up again when we got to chlorine, and we finally get all the way across to neon. We have now completed the second energy level, right? We have filled those 4 spaces with 8 electrons. If I want to go to sodium, right, that next electron will have to go out to the third energy level. When you go to the third energy level, you introduce a new shape, the D shape. There are 5 orientations for a D. So when you get to the third energy level, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 places to put electrons. And that next electron will go into that lower potential energy 3s orbital, 3s position. When I get to magnesium, there's still room in the 3s to put 2 electrons, so they'll double up. And then I'll do the same, right? I fill in pretty much the same way I did the second period, right? I go across, right? So filling in the P's, they fill in the same way, right? They singly occupy before they have to double up. I go all the way across, and I have filled the third period. Now notice, right? The third period represents the third energy level. I got spaces left over in the third energy level to put electrons. Yet, when I get to potassium, I start putting electrons further out into the 4s. Electrons go into the 4s with potassium before you start putting electrons into the 3d. Now, why is that? It has to do with the shape. Because of that 3D crazy cloverleaf shape, it's a higher potential energy shape than either the P or the S. It's such a high potential energy shape that it's even higher in potential energy than the 4s. So when you get to potassium, you start putting electrons into the 4th energy level, the 4s, before you start putting electrons into the 3d. So there's still room there on the 4s to put another electrons. When we get to calcium's electron configuration, we'd have 2 electrons in the 4s. And it's only when we get to scandium that I start putting electrons into the first transition series, right? 5 orientations for a D shape. So 10 electrons can fit in this 3D. And if you count the boxes across with the first transition series, we have 10 elements. So scandium, this is the first element where you start putting electrons into the D shape, right, the 3D. And then you get to titanium, right, Hund's rule, it would rather be singly occupied. And then you get to vanadium, right, you start putting 3 electrons, 3 unpaired electrons in the 3D for vanadium. And then we get to chromium. The expectation is, if you notice what happened, going across nice, right? 2 electrons in that 4s, watch that 4s box. When we get to chromium, and now it's 4s1, 3d5. Why is that? Well, because what's happened is because the number of protons that you keep putting into the nucleus, you've now pulled that 3d down so that the potential energy is the same in the 3d as it is the 4s, and Hund's rule takes over. So this is called an anomaly, right? You expect 4s2, 3d4. In reality, you get 4s1, 3d5. Then we get to manganese, right? I put the electron back on the 4s. All right, so I'm back on track again, and I start filling them in, right? So iron. Looking at this version of the periodic table, the way this is laid out is according to electron configuration. If you're in group 1A and 2A, this is where the S's fill. If you're over in group 3A, 4A, 5A, 6A, 7A, 8A, this is where the P's fill. If you're filling in from scandium to zinc, those 10 elements, this is where you're filling in the D level, right? So the 3D fills, and below that the 4D and the 5D, and those overlap with the 4s and the 5s. So the way we put electrons into configurations is we just follow the periodic table. All right, so first the 1s fills. All right, helium's over on the side of the noble gases because that's it, right? Those are the outer electrons for helium. And we'll talk about outer electrons in a second. So the 1s is filled. Now you fill the 2s. After the 2s fills the 2p. After the 2p fills the 3s. After the 3s fills the 3p. Now here's the weird one. The 4s fills before the 3d. Once you finish filling the 3D, right, once you've put in 30 electrons to get zinc's electron configuration, then you start filling the 4p. After the 4p, you go down to the 5s, and then the 4d, and so on. So amazing, right? The electron configuration matches the chemical behavior of the elements. So even before we knew where electrons were, we were able to arrange this periodic table, but now it matches up with where the electrons are in the atom. Lithium, you've got 3 electrons to account for, right? 2 of them go in the 1s. That's now filled according to the Pauli exclusion principle. That next electron has to go out to the next energy level, and you find it in the 2s. So lithium is a 1a metal. It has 1 electron, its outer level. So this brings up a shorthand way of writing electron configuration, right? We can do the box notation, which is useful in terms of unpaired electrons, right? Lone electrons. It's what chemistry is all about, right? Lithium loses that 1 outer electron. So one way of expressing this is to write 1s2, 2s1. Electron configuration written this way shows the distribution of electrons in the ground state of the atom. Each component consists of a number, which indicates the energy level. So in the first energy level, you only have 1 shape, and we can put 2 electrons in that 1 shape. So the S stands for the shape, the 1 stands for the energy level, and the superscript stands for how many electrons you have in a particular shape. So 2 electrons in the 2s, 2 electrons in the 1s, 1 electron in the 2s. So written either way, right? They mean the same thing, right? Where the electrons are around the atom. So like I said before, there are inner electrons, core electrons, right? So the electrons are on the inside when you're in the 1s, and then there's outer electrons, right? The ones out in the furthest energy level. These are also referred to as valence electrons. And guys, in chemistry, it's about the valence electrons, the electrons on the outside. Lithium loses 1 electron in chemical reaction. It's that electron out in the 2s that is lost. So a way of writing electron configuration using what's called the core notation. Whatever electrons are in the core, you write the noble gas configuration, right? If we go across the 1s, that's a helium configuration. 2s2 is the same thing as a helium configuration. So brackets around helium. 2s1 is another way of expressing electron configuration for lithium. Again, like I said, core electrons block the outer electron from feeling the nucleus, right? It's electron-electron repulsion. This is why the outer electron on lithium is so easy to take off. It's got inner electrons blocking it from feeling the nucleus. So if we're going to beryllium, right, we have 1 more electron we can put into that 2s, all right? So 4 electrons for the 4 protons that are in the nucleus. Once we get to boron, I start putting electrons into the 2p. So again, I've got a helium core, 2s2, 2p1. If I'm talking about carbon, it's 2p2. If I'm talking about nitrogen, it's 2p3, and then 2p4 for oxygen, and 2p5 for fluorine. And then when I get to neon, I have filled the 2p. At this point, if I'm going to put another electron in for sodium, it goes out to the 3rd energy level. So now we have a different set of core electrons. We have 1s2 filled, 2s2 filled, and the 2p filled. Those are the inner electrons. The outer electron for sodium is out in the 3s. So a way of signifying what the inner electrons are is putting brackets around neon, right? That's at the end of the 2nd period. And now I'm starting over. I'm putting electrons now out in the 3s. So neon core, 3s1.